So, in this lecture we start considering rocks, which are very useful for making stuff with, so are well worth understanding. So rocks are all comprised of minerals. Remember minerals, and there are three main types: igneous, metamorphic, and sedimentary. Note all the green arrows. So this lecture will be about igneous rocks. So igneous rocks are from cooling of magma or lava. Molten rock from below the Earth's surface has come up and either been placed into the Earth or come up on top of the Earth. And they can be divided by chemistry, for one thing. This includes felsic or acidic, intermediate, mafic or basic, and ultramafic. It can also be divided by where they cooled. This is basically the same chemistry, but it looks very different in that this is very fine grained and this is very coarse grained. This screen is about 2 millimeters across on this image. But they have the same minerals. These are a mineral called plagioclase, and this is a mineral called pyroxene, clinopyroxene, probably augite. And this is exactly the same thing. Here's the pyroxene, and here is the plagioclase. And so this has cooled under the ground and taken a long time about doing it. And this is cooled on the surface of the lava and has cooled rapidly. So, as I've told you before, igneous rocks include volcanic and plutonic. So, volcanic and plutonic. And so, intrusions to archaeologists, however, are different. So, if you have a good archaeology background, you might be confused by the idea of intrusions. Both geology and archaeology have strata, but for geology, intrusions come from beneath and come up into the strata, and in archaeology, they come from higher and go down deeper. In each case, they are emplaced after the surrounding environment, the country rock, as it's called in geology. So this is a lot of information on this graphic. I spent part of this afternoon making this, so I hope you enjoy it. But it's very informative. Here you have all the major igneous rock types and what makes them up. So here it's divided into the main divisions of felsic, intermediate, mafic, and ultramafic. And this is partly based on silica content. See along the bottom here, you see, this is more silica and this is less silica. And the silica we can found in all sorts of minerals. Quartz, of course, you know, is entirely silica, and that's down here. Whereas all these other minerals are silicates. Remember the silicates? And so they'll have less and less and less until you get down to quite a little. And you can see that they also have the main names of the intrusive and extrusive rock types. Some of these will be very familiar to you. I'm sure you've heard of granite, very useful for putting on the sides of buildings, very popular in downtown Toronto. Basalt, I bet you've heard of. Some of these you won't have heard of. Andesite you may have. Komatiite, for instance. I'm sure you have not heard of this unless you have a geology background, because it's actually quite rare. Now, another aspect of this is as the silica goes down, there's increasing amount of magnesium, iron, and calcium. So this is where you find these, what I've referred to before as ferromagnesian minerals, with Fe and Mg, ferromagnesian minerals, like amphibole and the pyroxenes and olivine. As a consequence, you'll find that the more mafic a rock is, the darker it is. So it's really quite easy to look at an igneous rock and say, oh, that's quite a light-coloured igneous rock, so it must be over here. And so, oh, that's quite a dark igneous rock, and that must be over here, even before you identify the minerals. So we'll go through each group: felsic, intermediate, mafic, and ultramafic. So another way of looking at it is this ternary diagram. And not a lot of people other than geologists do ternary diagrams. They're tremendous fun. This one has quartz, alkali feldspars, and plagioclase. And so the more that a rock will have of each, the closer it will be to each corner. So a rock which is entirely made of quartz will be up here somewhere, which is a very rare rock, as an igneous rock. It's quite common as a sedimentary rock, of course. And so here you will have granite, which is roughly equal amounts of quartz, alkali feldspars, and plagioclase, and then you'll come down to the gabbros and the diorites. Of course, the distinction between gabbros and diorites will be the amount of ferromagnesian minerals, but they're both down here with lots of plagioclase in. This is the same diagram with the volcanic rocks, and so you can see granite is rhyolite. And these are some of the other rock types that you really don't need to worry about too much at the moment. So granitic rocks, or felsic rocks, or rhyolitic rocks, will have a lot of potassium feldspar in, and a lot of quartz. So these occur, of course, in near subduction zones where you have the melting of the subducting plate coming up to the surface and being in place as batholiths, intrusions, plutons, whatever you want to call them, and some will come up to the surface as volcanic rock. Here is a thin section of granite. A thin section, of course, is a piece of the sample which is 0.03 millimeters thick, and which enables you to look at it through a microscope which has polarized filters. And when you have two polarized filters, this should actually be completely black, and you can see some of it is black. But elsewhere, the light is refracted by the minerals, and this actually creates these colors. These colors are just the natural color of the mineral. This is in plain polarized light. So in here there is quartz. This is probably quartz here. Orthoclase. I think this is orthoclase here. Plagioclase. Orthoclase is, of course, potassic feldspar. Plagioclase. This is a plagioclase here. And also amphiboles, including hornblende, which is just a very complex hydrous ferromagnesian silicate. This will be the amphibole here, and this one here. There will be muscovite, the mica with no iron in it, and also biotite, the iron-bearing mica. This is biotite right here. See this one here? It looks quite similar, but if you actually take the polarized light microscopy course, you will easily be able to tell the difference between this mineral, and also this mineral and this mineral. So granites are very popular for making things out of. They're very robust rocks, quite easy to work. If you can actually just like get another piece of granite and bang it away until you make them both smaller. Probably the most famous granite is the Aswan granite, which I've told you about before, with its very distinctive pink potassic feldspars, very large feldspar inclusions. So the felsic volcanics include rhyolite and also include pumice, which you may use for cleaning your bits, and obsidian, the volcanic glass, which would, of course, be very nice and shiny, and you would use for making tools. And, of course, I've already told you a bit about how the trade in tools is why Çatalhöyük became such an important center, making weird shrines and women with cats. So then you have the intermediate igneous rocks. A lot of plagioclase. You can see there's lots of plagioclase here, and some other things like amphibole. So basically, this is going to be a very grey rock. Here in this area, so this is that type of rock on the this ternary diagram down here near the plagioclase. This is a good example. This is what you often find in Egyptological literature as black granite. And of course, there's no such thing as black granite. This will be some sort of intermediate igneous rock, not a granitic rock at all. So gabbro, basalt, the mafic igneous rocks. A lot of plagioclase again. And a lot of pyroxenes, an awful lot of pyroxenes. Very dark rock with all the pyroxenes. And also some olivine. And of course these occur where you have oceanic crust over, or even where you have the continental crust over an upwelling of magma from below the crust. So this direct access here will produce mafic volcanism on the surface. And go back to these and remember an intrusive rock like this, which you will get a lot of, gabbro, and the basalt here will have plagioclase, lots of plagioclase and clinopyroxenes, and also olivine. This is a big piece of olivine in a basalt. So you can see the fine-grained matrix made of plagioclase. There's also magnetite, iron oxides in here, and also pyroxenes. So basaltic lava, of course, is very active, very dangerous, and you don't want to mess with it. But you can make some quite nice things with it if you're so inclined. The very well-known Rosetta Stone seems to be made of basalt. And in Syria, where I took this photograph of these shield volcanoes, we have in northern Syria quite an extensive basalt flow area where you get things like this. This is actually from the Middle Bronze Age palace in Aleppo on top of the large castle there. And you can see in this, it's actually a temple, not a palace, all these basalt parts of the walls. Very nice. So then we have the ultramafic rocks with a lot of pyroxenes and an awful lot of olivine. So olivines, the ferromagnesium silicate par excellence. Well, what is possibly more interesting to the studiers of stuff is when you get these things being thrust up onto the Earth's crust, as we have in the Middle East with these thrust zones, which, because of the collision of the Afro-Arabian Shield and the Eurasian Shield, have produced what is known as an ophiolite sequence. So here you can see the opening of a mid-ocean ridge. And so what happens is, as this comes up, you have lava coming out of the top. Lots of lava, great sheets of lava. And then you have these dikes of gabbro in between, and underneath will be the oceanic, will be the magma, which cools. And so you have the basalt, you have the gabbro, which is basically basalt, which is cooled at a lower, cooled less rapidly. And underneath that is the peridotite, which is the magma, undifferentiated. So the olivine will often, under such circumstances as being thrust up onto the surface, turn into two quite useful minerals. Serpentine, which we met in the last lecture, which is quite a useful stone, and magnetite, iron oxide, which is a very useful source of iron, of course. This is actually footage of pillow lava being formed. This is what is on the surface of the deep ocean, where these basalts come up to the surface and they sort of squish like toothpaste out into the sea, where it cools rapidly because it's being pushed out into the sea. So in this environment, of course, you get, here's some pillow lavas, as they're called, because they look like pillows. Not very comfortable. So around here, of course, as I said in an earlier lecture about these sulfur vents, you will get a lot of very useful metals. So associated with these thrust zones, with this ophiolite sequence, you will have a lot of very interesting materials like copper and, of course, iron and things like that. So it's a very useful rock in a way. So hopefully this diagram is now like interesting to you, and that you look at it and think, oh, this helps me understand igneous rocks so much better. So have a study of this, and I'll get back to you about other types of rock.